Hi guys, welcome back to my mathematics tutorial. My name is Peter C. Dogba Jr., mathematics instructor of the University of Liberia and your math tutor. In my today's lecture, I will be discussing differential equations, and particularly I'll be looking at solving differential equations using variable separable method. So we said in previous lessons, when you have a differential equation where the variables can be separated on separate sides of the equations, then you can use variable separable method to find a general solution by integrating both sides of the equation. So let's look at the next example problem. So if you have some issues in understanding this topic, you can watch previous videos so that you get better understanding. So we have ln of dy by dx equals to ax plus by. So in order for us to get rid of this ln, we must bring in the property of exponential function. We know that e raised to the ln of x is just equal to x, or this x could represent any function or just anything. So it is similar to this expression. If this is ln of this expression, or this thing that is right in here, to get rid of this thing, you have to say e raised to the ln of what is in there, dy by dx. So since we say e raised to this on this side of the equation, we must do the same on the right hand side of the equation by saying e raised to ax plus by. So now e raised to the ln of dy by dx is just equal to dy by dx, and then e raised to ax plus by, we can separate it. Since we have x and we have y, we can separate. So it's e raised to ax times e raised to by. We cross multiply, you will have dy equals to e raised to ax times e raised to by dx. So since this is dx, we only need an expression in x, so we must divide both sides by by e raised to by. So this will cancel. So we can send this one in the numerator, e raised to minus by dy equals to e raised to ax dx. Since the variables have been separated, we can integrate both sides. So we know that the integral of e raised to ax dx is just equal to 1 over a e raised to ax plus some arbitrary constant c. So we can apply that. So now this a that is right here is represented by minus b. So you have 1 over minus b e raised to minus by equals 1 over a e raised to ax plus some arbitrary constant c. So we can multiply all sides by minus b to get rid of this b down here, so that would be able to solve for y. So b times this one is just equal to e raised to minus by equals b times this is just minus b over a e raised to ax minus b times this one is just bc. So now to get rid of, let's say to solve for this y, we have to take the ln on both sides, because we know that the ln of e raised to x is just equal to x. So the ln of e raised to whatever it is raised to is just equal to that particular exponent minus by equals to ln of, so we take the ln of this entire thing minus b over a e raised to ax. Now this bc is still a constant, so we can just represent it by one constant. So we say plus a. So this is now equal. So we read the positive first. So this sign, we change this sign because it's just a constant. So whether positive or negative, the fact is that when you differentiate this constant, you're going to get 0. Whether negative or positive, you're going to get 0. So that's the reason why it's not important whether it's negative or it's positive. It's still a constant. So we can write it first. We have the ln of a minus b over a e raised to the power ax. So if we just divide both sides by um, minus 1 over b, you understand that you have y to be equals to minus 1 over b ln of a minus b over a e raised to the power ax. So remember now that this is the exponent of the argument of the natural logarithmic function. So that can be written as ln of a minus b over a e raised to the power ax or raised to the power negative 1 over b. So finally, to change this sign to positive, we can reciprocate. So y is just equal to the ln of 1 over a minus b over a e raised to the power ax raised to the power 1 over b. So this is a general solution of the differential equation ln of dy by dx equals to ax plus by. So thanks all so much for watching. See you in our next lecture. Thank you. Please subscribe. Don't forget.